Every Edibon product is designed, manufactured, and quality controlled at our headquarters in Madrid, Spain, under several quality standards. In this video, we will be discussing the photovoltaic solar energy unit, which is called the EESFC. It is a computer-controlled unit designed for the study of the transformation of solar energy into electrical energy. The photovoltaic panels use the photoconversion law for the direct conversion of solar radiation into electricity. However, there are many elements that can affect the magnitude of the power that is generated by the photovoltaic panels. Varying these elements allows the user to get a better understanding of how the system functions as a whole. The elements that can be adjusted in this unit are the magnitude of solar radiation emitted from the solar lamps, the light's angle of incidence on the solar panel, series or parallel configuration of the panels, panel ventilation using a row of fans, the location of the solar radiation sensor, the load connected to the photovoltaic panel, and whether the load is being powered only by the panels or if the panels are being assisted by a regulator and battery. The battery charger, 12-volt battery, charge regulator, and load module box are all securely attached to a steel panel. Let's take a closer look at the load module box. This is where the load can be changed. The 4-position dial allows a system to power no load, 2 lights in parallel with the rheostat, the lights and rheostat individually, a DC motor, or it can bypass this interface box so that it can be converted to AC and used in the optional EE kit and EE kit 2, which is used to simulate injecting the energy into a power grid. This unit is supplied with a SCADA computer control system, which is patented by Edibon and based on LabVIEW. This system includes the physical unit, a control interface box, a National Instruments data acquisition board, and a software package that allows computer control, data acquisition, and data management. I will now perform a quick demonstration to show the operation of this unit as well as its teaching potential. Before we start the experiment, I will explain the layout of the user interface. The main controls are in the upper left corner. This includes the calibration, start, stop, view data, and quit button. A schematic diagram shows the layout of the components in the system. When you start the system, the screen will look like this. The sensors are located in the upper right. This includes room temperature, temperature on panel 1, temperature on panel 2, solar radiation striking the panel, generated voltage, and generated current. If the optional kit is included, it will also display the AC voltage and current. The actuators are located on the bottom right. This is where the radiation emitted by each set of solar lamps can be independently controlled. The panels can be connected and disconnected from the circuit and arranged in series or parallel. The fans can be turned on and off. The panels can be connected to the system before or after the regulator. The interface can display 2 independent graphs or 1 large graph using the drop-down selection. The parameters that are displayed on the graph can be selected in the bottom left region. Alright, let's begin. In this experiment, we will maintain constant solar radiation while varying the load using the rheostat to see how it affects the current and voltage. First, make sure that the panels are set to parallel. The panel is connected to the load before the regulator. Panel 1 is on, and that the current and voltage are being displayed in a single graph. Now start the system. Choose a name for the data file and click OK. Set Sun 1 to maximum radiation. Once the sensor values have stabilized, start saving the data. Now we will slowly vary the rheostat from maximum resistance to minimum resistance. The change in current and voltage can be seen on the graph in real time. Now that the data has been recorded, stop the system and view the data. Choose the named file and select the Signal versus Signal tab. With the chart displaying current versus voltage, we can clearly see their relation to one another as resistance is varied. The user can clearly visualize the location of the maximum power point of the photovoltaic panel. The user manual provides multiple practical exercises that walk the students through the correct operational procedure while teaching specific concepts. A non-computerized version of this unit is also available. It displays the current sensor values but does not have data acquisition capabilities. Only Edibon has a SCADA system that provides the following benefits: open control, multi-control, and real-time control. This means that at any time during an experiment, multiple parameters can be changed at the same time with instantaneous effects on the unit. Each unit has specialized software based on LabVIEW to enable easy control of the unit. Calibration exercises, which are included, teach the user how to calibrate a sensor and the importance of checking the accuracy of the sensors before taking measurements. Projector and electronic whiteboard compatibility allows a unit to be explained and demonstrated to an entire class at one time. The system is capable of being remotely controlled over the internet by the user or by an Edibon technical support engineer. Each unit has 4 safety systems that are designed to mitigate risks for the user. This unit has been designed for future expansion, such as incorporating the unit in an Edibon SCADAnet system, which enables many students to simultaneously operate any unit in their SCADA network. The